Let me welcome you again to another section that is talking about dynamics. Not really a section, it's actually a module. So this module we are dealing with dynamics, and we have some objectives that we'll be focusing on, and I will want you to know a little about them. The first one is about the Newton's laws of motion and some formulas for weight and some basic knowledge about weight, frictional force and inertia. We'll do some calculation on work done and power. We will also state the law of conservation of energy and the concept of it when it comes to potential energy and kinetic energy. Do calculations applying this information that is above. Now let us start with definitions. Let's talk about what Sir Newton Isaac told us. There are three laws that are from Newton. So the first one says a body will remain in its state of rest or uniform motion in a straight line unless is acted upon by an external force. The second law says the rate of change of momentum of a body is proportional to the applied force and is along the line of action of that particular force, of the applied force. And finally, the last law says action and reaction are equal and opposite. Now, obviously, we will see how we apply these three laws as we go along when we explain some few formulas. But before I go to those formulas, let me start with the formula sheet that you get in the exam room when you are writing. So under this module, you will notice that the only formulas that are there are basically these ones. These are the formulas that you will see when it comes to dynamics. Maybe you can add that one. Yeah. So these formulas of motion, of course, they can be applied anywhere where we talk about dynamics, when we talk about angular motion, sometimes, yeah, anything that talks about motion, we can apply these formulas. So they're not really basically for this module only. Then we have power. We have the formula for power because we heard from the objectives that we need to know to calculate power. So power, P is for power, F is for the force, V is for velocity. Obviously, V is velocity, U is okay. For this particular formula, V can either be U or V. So V is final velocity, U is initial velocity, A is acceleration, T is time. Final velocity, initial velocity, acceleration. Now S is displacement. Now remember, we have the formula for work done as well, which is force times distance, but it's not here. We have distance or displacement, initial velocity, time, acceleration back to time. Then this P is for power, F is for force, V is for velocity. FA is for accelerating force, M is for the mass, M is for the mass throughout. A, just like there and there and there, is still for acceleration. Then we have our two energies. We heard from the objectives that we should know the concept of the law of conservation of energy being applied when we talk about potential energy and kinetic energy. Obviously, by definition, potential energy is an energy at rest when we consider the height. Then kinetic energy is the energy in motion or in respect of velocity. So this is why we'll have velocity going with kinetic energy and height going with the potential energy. That G is for gravitational acceleration. So that's what we have when we come to the formula sheet that we'll get with the question paper. Now let's move to the one that I've derived so that we may do our work a little easier. In other words, most of these formulas you need to memorize them. You definitely do not need to memorize 1, 2, 3, 4, because these ones are already in your formula sheet. Okay, maybe except that one, but you might not really use it anyway. This is also in your formula sheet, FA is equal to MA. Then this is not in your formula sheet, where we have FT equaling FR plus FA, or simple FA equaling FT minus FR. What does FA stands for? I already told you it's the force due to acceleration. FA, force due to acceleration. FT is the force, is the attractive force, or the force that is applied. Then we have FR. FR is the force that resists motion, so it is against movement. It's more like frictional force. In fact, it is the frictional force. That is the FR. Then we can talk about the braking force. Now the braking force, you will notice that it's here. All of this section is for braking force. Now the braking force, when we have FT and FR, then the braking force will equal to FT minus FR. When we do not have FR, the braking force will equal to FT. Then if we have FA and FR and we do not have FT, then the braking force will equal to minus FA minus FR. And if there is no FR, obviously it will just be negative FA. So that's what we have when it comes to the braking force. I hope it makes sense. FB plus FR is equal to FT. So in other words, we can have FA equaling mg sine theta minus FT. So that's what we may have for some other formulas, or we can just put that one if we do have the braking force and not FT. So in other words, for this one we can have that. Then FA also can equal to FT minus mg sine minus FR. Still following the concept of the braking force, now we come to these ones. But this is what we're talking about when we're referring to the law of conservation of energy in respect to the potential energy and kinetic energy, because now we will have the potential energy equaling the kinetic energy. That means the loss in potential energy should equal the gain in kinetic energy. That is the conservation of energy. That's the law of conservation of energy at work. Now this is done when we are not given the frictional force. We can use this. But if we are given the frictional force, then now we should include the work done against friction. So that means we'll have our potential energy equaling the loss in potential energy will equal to the gain in kinetic energy plus the work done to overcome friction. You know the formula for work done. Work done is equal to force times distance. So it will be our force will be Fr times whatever distance that is given. So that will be your force. So the distance obviously to be the distance along with the force, that is in the same line of action of the force, because this is work done. Work done goes with the distance that is in the line of action of the force. Alright, this is what we have. This is without friction. This we use it when we have friction. That's the difference between the application of the law of conservation of energy. At this point, I think I have explained everything I needed to do when it comes to basic formulas. Now I think we will move to some specific formulas in this module. We have friction. We have this statement that is very important: friction resists movement. Therefore, for an object to move, a force must be applied to overcome friction or to overcome this resistance. So that is why we should talk about the forces. Obviously, this falls under the first law of Sir Isaac Newton. Now, what about this one? This is momentum. P is momentum, and this is the formula for momentum. But we know that the second law, it says the rate of change of momentum is proportional to the force, and that is the second law. This is the rate of change. The term rate means divided by time. So that means the rate of momentum is proportional to F, to force. So that will be the law 2 of Sir Isaac Newton, which is force equaling ma, which is this accelerating force. Then obviously this will definitely okay, I can say maybe this one is definitely the Newton's third law, because forces on the one side should equal to the forces on the opposite side. That is what we have under that section. Now we have moved here and we need to talk about the specific formulas that we can use. If we dynamics is basically about two types of movement, because the term dynamic, it talks about movement by itself. So we are talking about two types of movement. We have horizontal, and we also have movements that are at an angle. We call them incline. So let's start with the horizontal, because horizontal is more basic and very simple in nature. Assuming that we have this horizontal plane with this body, or the mass of the body, or this body of mass, this is the weight, obviously, because it's exerting a weight on top of this plane. Now we have Ft and Fr, because we said Fr, friction, always opposes motion. So Ft being the force, the attractive force, or the force that is applied to cause motion. So if Ft is moving in that direction, Fr will just oppose it. And there is the weight, but we won't really focus on the weight at this point, because the weight does not already have, and we will not be looking for NR. So that is why we will not be focusing on this one. So this is Newton's third law. Ft equals Fr, Newton's third law, and is very applicable when we are talking about constant velocity. When I talk, okay, the constant velocity is when an object is already moving, but it's not accelerating, it's just moving according to Newton's first law. it's just moving, no acceleration, then we can say Newton's third law also apply, because Ft should equal to Fr when there is no acceleration. What if there is acceleration? Then for acceleration, obviously we will have Ft equaling Fa plus Fr, or simply put, Fa will equal to Ft minus Fr, and also Fa will equal to Ma. And remember, we saw this in our formula sheet, so this basically is the only formula that is in the formula sheet. So let's be specific. What do we mean by Ft? Force required for motion, or the tractive force. What about Fr? Is the force resisting motion or the tractive resistance? What about Fa? Fa is the force to accelerate, or just the acceleration force. That's about it when it comes to horizontal movement. Now let's quickly move to incline movement. Wow, wow, and wow. Okay, so this is where we are now. At this point, I would like you to reflect on what we have talked about already. If you have any questions, or you think you do not understand anything, make sure you ask questions, because I really want to help you out, and I will definitely not be able to help you if you are not making it easy for me. When you ask questions, you are making it easy for me. So you ask questions, and you will also make me to explain things I thought they were so common such that they didn't need explanation. But when you ask questions, then you'll make me explain those small things, or those things that are considered by other people as basic. Then let's go to this diagram now, because we're focusing on the inclined planes. Let's go to this diagram. We have this plane, we have a mass on top of it, but now it forms a certain angle. Now we have the weight, and that weight obviously you can see is not perpendicular to this angle as we had it here. Can you see the weight here was perpendicular to the plane, but in this case the weight is not perpendicular to this plane. So because the weight is at an angle to the plane, as we usually do, remember, we usually do this when we have maybe a force that is at an angle. We usually resolve it into components, which are horizontal and vertical component, and we will have an angle right there. Then that will be what it looks like. So we usually put it in terms of the horizontal component and the vertical component. If, of course, that was F, so obviously we would have F cos theta, because this is theta and that is F, so we have F cos theta on the adjacent side to the angle, and on that opposite side to the angle we'll have F sin theta. Okay, so remember, the side that is adjacent to the angle, we will have cos. Now this is our angle. This side is adjacent to this angle. That is why it is cos. So it's mg cos, or simply put, weight times cos theta. Now this side is opposite, or is going in that direction. That means it is going along this line of action. So this one will be our mg sine theta. So it always goes in that direction. ft and fr can change. They can change places, but we know that they are always opposing each other, but they can change places. So if this becomes fr, then that means that is ft. So that's how they do. They always oppose each other, but mg sine theta, which is the red one, will always go in this direction. It will never go up. It will always slide down. It will assist the block to slide down. That is mg sine theta. Mg obviously is the weight, sine theta is the slope in our case. We won't really focus on mg cos that we won't even be like talk about it, because we won't focus on it at all. To us, this does not really exist. We'll just throw it out of the window. Then obviously this angle is the same as that one. If you do not know it, the angle similarities when we were doing mathematics in those days, yeah, they are similar in that format. Let's talk about fr, that force. Basically this force equals to mu times the weight times sine theta. So mu times the parallel component of this plane. So that's what we have, parallel component of the weight. That's what is equal to F mu, or force due to friction. Alright, now when we're dealing with the horizontal movements, we had two types of concern. We have the constant velocity concern, we also had acceleration concern. So even here we have two types. We have the constant velocity concern where we have a equaling 0, but now we can see we have two directions, down and up. So ft can either go down or go up. Now if ft is going up, let's look what formula we're gonna have. Ft will equal to mg sine theta plus fr. Yeah, of course it makes sense, because remember mg is this force, and now we just changed this fr and it became ft. So we have ft here, and now this is our fr, because they always oppose each other. Mg sine is always there. So if this is ft, then fr and mg sine are in the same direction. We can just add them. That's why we have them added right here. Then what about for downward movement? For exactly what we are seeing there, obviously mg sine theta this time is in the same line with ft, and we were making ft the subject of the formula. Obviously it will go to the other side and become negative, because now it's added to the force that is going in this opposite direction. So the sign, it only means that we are going to the opposite direction. That's what it means. Then we are done with constant velocity or acceleration between 0. Now let's look to the second concern, which is about acceleration. Also we have up and down. Now for acceleration, if we have this formula, we'll just add acceleration there. We'll just say plus acceleration. This is what we have there. We just said plus acceleration. Okay, but and then the only difference is that here we made acceleration the subject of the formula. So when you make acceleration, which is the plus acceleration, the subject of the formula, you take both of these to the other side of the equal side and they become negative. I think that makes sense. So we will do the same thing for downward. We'll just add the acceleration right there. So we'll just add FA and make FA the subject of the formula. Then that means this will cross over and become positive. This will cross over and become negative. Now you might be wondering, why do I have FR in red? It's because it's on top of the tomatoes, rotten tomatoes. Okay, I'm just joking. It is because it can be ignored if it's not given. For example, if in the information you only have FT and the weight with the angle, you can just use these to find FA if there is no frictional force or there is no mention of friction. So if they didn't mention friction at all, ignore it. Don't bother yourself. That's how it goes. And then let's move to the braking force. Now for the braking force, I will not dwell to it the way I did here. I made sure you understand braking force here. I had 4 different formulas saying that if you have friction, you'll have these formulas. If you have friction and do not have FA, this is the formula to go with. If you have friction but you do not have FT, this is the formula to go with. If you do not have friction and FA, obviously this is what we will be doing. If you don't have friction and you still do not have FT, obviously this will be the one that you will be using for braking force. Then law of conservation of energy, without friction, there's no friction again here. If there is frictional force, then we will look for the work done first, and then this will be the formula. So both of these formulas are for the conservation of energy, the law of conservation of energy. Right, then let's continue with what we're talking about. This is the braking force. Now what about inclines? How can they be written for us? Okay, so they can be written as a ratio or as a percentage. For example, if it is a ratio 1 in 12 or 1 in 120, you can just use this. But if it's 1 in 120, for example, you will just say this tan theta. You can say this tan theta is equal to sine theta if this was 120. And for the percentage, this will be what we'll be focusing on. Obviously, in here we can say this tan theta is the same as sine theta, because if you can press your calculator, you'll notice that they are basically the same to the second or even third decimal. So that is why they can be equated just like that. Guys, so this is what I was talking about, guys. For example, if we change this 12 to 120, that will mean we will have this equal to sine theta. In fact, even here we can say this is equal to sine theta, because maybe to the second decimal they really resemble each other. So we can say tan theta is basically equal to sine theta. Here it's really equal, I mean to the third or even the fourth decimal. So these ones, they are definitely equal, especially in our calculation. So for calculation purposes, we can just, if we are given the ratio, the incline in terms of a ratio, we can just say it's equal to sine theta. Same goes for the percentage. You can just say it, you can just change that percentage into a ratio so that you can equate it to sine theta. So that's what you will do when it comes to ratios. Guys, let's meet again to the next video, because I don't want to have a very long extra long video. This is fine for now. I try to unpack the basics of dynamics. So now let's go to calculation. God bless you. Bye bye, and I love you.